Number 6. A nurse injects 71 cc's, 71.0 cc's of medicine into a patient. How many liters is that? Will got his tetanus yesterday, right? Some come up here. Got a shot yesterday. Wonder how many cc's that was. 71 cc's is how many liters? Give me some statements of equality that's going to move us from cubic centimeters into liters. cc's into liters. Give me one of them. Somebody with a hand. Yes, ma'am. 1 cc equals 1 milliliter. Good. That's the definition from the book, right? 1 cc equals 1 milliliter. What's another one we're going to need? Because we're moving from cc's. Using this, it'll get us to what? From cc's to milliliters, right? Are we asked for milliliters? We need to figure out some relationship that's going to get us from milliliters to liters. What would that be? 1,000 milliliters. Hands, please. Gray.
1,000 milliliters in 1 liter.
Okay, so 1,000 milliliters is 1 liter. Remember, the milli means thousandth. So what this is showing you is you need 1,000 one-thousandths of a liter, which is 1 liter, equals 1 liter, right? So those are my two relationships. I can go from cc's. I start with cc's, and I can go from cc's to milliliters, and I can go then from milliliters to liters. So I've got everything that I need to create the conversion factors to move me all the way across to liters. So I'm going to write down what's given or known, 71.0 cc's, a conversion factor that goes from cc's, in this case we know milliliters, it's a 1-to-1 relationship, and then from milliliters to my unit I'm asked for, liters, in a relationship of 1,000 to 1. Did I really technically need to show this step? No, not really, a 1-to-1. I could have just written 71 cc's equals 71 milliliters and gone on from there and started just with milliliters. But this shows both steps if you weren't positive about that. It's not always going to be a nice 1-to-1. That's why we have these statements of equality. So we do the math across, 71.0. This math is going to turn out to be 71.0 divided by 1,000. cc's cancel cc's, milliliters cancels milliliters, and I'm left with liters. When I do the math here, how am I going to, if I were to write this in decimal form, wait a second. All right, yeah, let's write this one in decimal form then. The shorthand way to do it. Yes, Ike?
0.071.
Okay, so I'm going to move the decimal, right? How many places am I going to move it in what direction? 3 places because there's 3 zeros, right? And which direction again? To the left, because I'm dividing by 1,000. I'm making it smaller. If I were making it larger, multiplying by 1,000, I'd move it 3 places, 1, 2, 3, but I'd move it to the right if we were multiplying. Here we're dividing, we're making it smaller. 3 places to the left. It's 1, 2, I need a place holding 0, and then I need a leading 0 to have it in appropriate form. So this comes out to be 0.0710. Now, let's look at that for a second and figure out, is that the correct way to write that answer? When we convert a decimal, or when we do this work, what precision are we looking at over here? Okay, and how many significant figures are we looking at? Those are 2 things I want you to first think about. Now we're dividing by 1,000, right? We're dividing by 1,000, but that 1,000 is by definition, so the number of significant figures or precision doesn't come into play. It's a definition, so we don't consider it. Look over here, and what can we say about this number over here? It's precise to the tenths place, and it is, how many significant figures does it have? 3 significant figures. So our answer must have 3 significant figures, right? Because our number here has 3 significant figures, there's no leading zeros, but there are 2 non-zeros. There's a trailing 0 right at the decimal, but there's no zeros between. So it's 1, 2, 3 significance. And I'm multiplying by a definition, which means I don't have to worry about it. It means my answer has to also have 3 significant figures. Let's look at our answer over here. How many significant figures are in this answer? Well, do we have any leading zeros left of the decimal? Yeah, we do. So we've got leading zeros over here. That's not 1. Okay. Do we have any non-zeros? Yeah, we do. Do we have any trailing zeros right of? Yes, we do over here. What about this one here? It's not significant either, right? Because it's not between two non-significants. It would be considered a leading zero, but I generally look at those as a second case. So it's not a non-zero, it's not between significants, it's not a trailing zero right of the decimal, it's a leading right of the decimal, it's not significant. So our answer here has 3 significant figures, and we needed to have it in 3 significant figures, so that is correct. 0.0710 liters. Okay. So the first part was the setup, getting you to this point here. The second part was, did you do it in the right number of significant figures? Again, I told you before, if you had 0.071, it's true, but it's not as accurate. It's not as completely correct as it could be. So that would be partial, but not nearly the bulk of it. The bulk of it is going to be getting to this proximity right here. Okay, that's my biggest concern. And if you did it correctly with the right number of significant figures, all the better. I'm clear to erase this? Okay. If you didn't get this before, especially if you asked the question, I hope you're writing this stuff down, right? Because I do occasionally let you use your notes for exams. So, and actually, I occasionally collect your notebooks and look at them while you take exams to see if you're taking notes. So that when I get an email or phone call from mommy who's upset that my class is too hard, and I can say, but he didn't take any notes. Hey, what do you want me to do with that, Mom? So just so you know, last year I used to grade the notebooks, collect the notebooks and grade them. So one of your grades, each module could be potentially your notebook. Because if you're reading it in advance and taking notes before class, and then in class you're adding to your notes, and then during class you're supplementing your notes, and after you turn in your homework you're writing down answers to things you didn't know, everything should be there in your notebook. And then when it's time for an exam and I say you can use your notebooks for this exam, people go, can I use my neighbor's notebook? I'm like, no, you can use yours. And we write it down, why? Because when you write it down, you're almost 80% more likely to remember it. Even if you think you know it. If you write it down, even if you think you know it, you're much more likely to remember it. That's why we do that. Number 4. If an object has a volume of 69.2 milliliters, so volume equals 69.2 milliliters, how many kiloliters of space does it occupy? So 69.2 milliliters equals how many kiloliters? So we know we need to go from milliliters to kiloliters. Do you happen to know a statement of equality that takes you directly from milliliters to kiloliters off the top of your head? Probably not. But because it's metric, we can always do an intermediate step that takes us through what unit? It's base unit, right? Whatever its base unit is. Here the base unit in volume is liters. So if I just assume that I can go from a unit to the base unit and from the base unit to my second unit, I know I have a conversion path. I can go in these steps. So I am going from 69.2 milliliters, and I assume I'm going to need 2 steps in my conversion, right? Because I'm going from milliliters to liters, from liters to kiloliters. So 69.2 times some conversion factor that takes me from milliliters to my base unit, and some conversion factor that takes me from my base unit to my requested ending unit, which is kiloliters. What will my units be? Well, milliliters cancels milliliters, liters cancels liters. I'm left with kiloliters, and that's what I've been asked for, so we're good. Kiloliters. Now I need to come up with my 2 conversion factors. Each conversion factor needs a statement of equality. to plug in there. So I need something that's going to relate liters and milliliters. So I need a statement of equality that relates milliliters and liters. So what would that first one be? Okay. Do I need to write it as an equals equation? Let me do it just for now. We will stop doing this after this module. But 1 liter equals 1,000 1,000ths of a liter. So 1 liter equals 1,000 milliliters. Take that and I convert it, or make a conversion factor out of it, so that 1,000 milliliters over 1 liter. And remember that the value of this whole thing is actually just 1. 1 liter is equal to 1,000 milliliters, so something divided by itself is 1. But what it's allowing us to do is basically convert it into the other language. We're translating it from milliliters to liters. That's what conversion factors do. So this right here will get us to this place. We need another conversion factor that's going to take us from liters to kiloliters. So kiloliter is equal to 1,000 liters. You may have worked this thing out. It's the same math written in a different way. Let me show you. That's the same thing, just written a different way. What I'm saying here is 1 milliliter is 1/1000th of a liter, and 1 liter is 1/1000th of a kiloliter. Okay, so I would have written these differently. This second way would have looked more like but we tend to think like this. This is the way I encourage you to think. If you're already thinking that way, that's fine. You can use it. Think like this, and that would create this top equation. And then we do the math. Again, so we're looking at 69.2 divided by a certain number of base 10, or a certain number that's going to be all zeros. 1, 2, 3, 4, 5, 6, right? So we've got 6 divided by 1 times 10 to the 6th power, which means we're going to move our decimal in our original number how many places in which direction? 6 places, and the direction being left. We're dividing. We need to make it smaller. So I'm just going to go ahead and preemptively draw a bunch of zeros up here. Okay? Let's go ahead and move it 6 decimal places. 1, 2, 3, 4, 5, 6. We'll keep that leading 0 because it's appropriate form. It's going to look something like that. Is it in its correct form? 0.0000692. We need to look back over, right, and figure out how many significant figures did we start with, because everything else here is a definition. So significant figures don't apply here. We just need to look at our original number, 69.2. How many significant figures? 3 of them. How many significant figures? 3 again. This is the right form. These are all there's no trailing, there's no betweens, only preceding. There's only 3 significant figures, so this is the right form in decimal form. It could also be written 6.92 times 10 to the 1, 2, 3, 4, 5, 6 to the -6th. These are the same thing. This is the answer in decimal format. This is the answer in scientific notation format. Okay? If it doesn't ask you for one form or the other, yes. Now remember, these are by definition. If these weren't definition, like if these were numbers that these were relationships that you came up with in the lab, then those number of significant figures would matter. The fact that they're by definition, they don't matter. Or they matter, but they don't count in terms of your answer. Also remember, if for some reason this was a 2 rather than a 1, what we'd be doing is taking half of this, 3, 4, 6, as this is opposed to 692. So any questions on number 4 then? Yes, sir.
Why is it -6?
It's -6 because my decimal place is here, right? If I wanted to take this number and write it as in decimal format, or excuse me, in scientific notation, let's see, first we're going to take it from this to here, right? So the process would be, here was my decimal. To put it in the correct form, I had to move it 6 places to the left.
Oh, so you don't start from 6.9.
You start wherever the decimal was before, 69.2. It was right here, right? It was right there, but I divided, in this case, I divided by, to count up the zeros, 3, 6. I need to move it 6 places. Moving it 6 places puts it here, which means my decimal moved to that location. Okay. Another way of writing this number, 0.0000692, is this. Because that's what I had to do. I had to move it 6 places to the left. As I converted this from a form that looked like 0.0000692 to the form that looks like 6.92, hopefully you see that this number here appears to be much greater than this number because of the decimal place. And because this number appears to be much greater, and yet it's equal to it, I need to signify that by making the exponent negative. Okay. So if I were to go from this, if we didn't know this, and we were just going from here to write it out in decimal format, I would write on my paper 6.92, and then do what I just did. Move it 6 to the left, and that would represent back in decimal format again. We'll be doing some more of this in 7 and 8 when we get to it, going from scientific notation to decimal and decimal back to scientific notation. So if you want to hold on to that review, I think that'll help us, okay? All right. So again, any fundamental issues with this problem we need to go over? Number 11. The average low temperature of International Falls, Minnesota in January is -7.0 degrees Fahrenheit. What is it in degrees Celsius? Again, hopefully you're picking up how to take a word problem and convert it to a math problem. Okay. So again, the word problem is the average low temperature of International Falls, Minnesota in January is -7 degrees Fahrenheit. What is it in degrees Celsius? So hand, do we have an easy way of doing this? Maybe that easy way of doing it? Like I told you, every time I write this down, I've got a mental block about this formula for some reason. I get it wrong sometimes. So I have to go back and plug in example numbers to make sure I wrote it down correctly. And I do that by using the freezing point and the boiling point. If I look at this number and I say, what is the freezing point? The freezing point is 0 and 32. Okay, if I plug in 32, 32 minus 32 is 0. 5/9 times 0 is 0. Okay, it works for the freezing point. Now let me go to the boiling point. The boiling point of water is 100 degrees Celsius. It's 212 degrees Fahrenheit, which makes this 5/9 times 180, because 212 minus 32 is 180. This is 1 that goes in 20. It's 100. Okay, my formula's right. Now I can use it. So I just check it for both cases before I ever use this formula, because I've been burned too many times in my own science classes by writing it down wrong. So I always check it personally. But you may sit there and go, hey, I don't have your baggage, Mr. Baker. I know the formula. This is the formula. Okay, cool. You're trying to figure out Celsius given Fahrenheit. That's exactly the problem here. Trying to figure out Celsius when we're given Fahrenheit. So all we do is go through and plug in the number. The Celsius value at -7 degrees Fahrenheit is 5/9. I plug in the Fahrenheit value. What is the Fahrenheit value? Negative 7.0 minus 32. Okay? So, is 5/9, what's my value going to be here? What's negative 7 minus 32? Negative 39. However, right, I'll go ahead and put this 0.0 in there. Because I was going to say, if you look back, how precise can you be? But this is by definition, right? So when you add or subtracting, you can only be as precise as your least precise, but I believe that they use... Actually, you know what? The answer key didn't go to that far. But I'm going to leave it because I think we're right, and I'll check on it. I'll think through the logic. But anyway, negative 39 or negative 39.0. Just so we get for that. Now we're going to go through and do the math. 5/9 times negative 39. I don't want to do that one in my head. It's negative 22. So negative 7 degrees Fahrenheit is equal to negative 22 degrees Celsius. Hardest part here was probably this, starting with a negative number and then subtracting a number. So on your number line, you would start at negative 7. 0, 1, 2, 3, negative 1, negative 2, negative 3. You're going to be starting at negative 7 and then moving negative 32 more, which would take you to negative 39. All right, questions? There being none? This is awesome. You know you're going to get at least 1, 2, 3 of them right or better, right? Because these were the ones you were all really concerned about. And there's been very few questions. So I'm assuming that you're speaking up if you have questions. I've got to assume that, right? If I give you the opportunity and you don't speak up, I can't help. Then let's continue for number 10. The temperature of the moon during the day, or during its day, is 396 degrees Kelvin. What is that in Celsius? And what is that in Fahrenheit? A couple different ways you could solve this one, but a way to think about it too. Is there an easy way for me to go from Kelvin to Celsius? Right. Correct. There is an easy way. We'll get to how to do that, but there is an easy way. Is there an easy way that we're aware of to go from Kelvin to Fahrenheit? No. Is there an easy way for us to go from Celsius to Fahrenheit? Yes. So our strategy should be pretty clear, right? We're going to go from Kelvin to Celsius to Fahrenheit. Why? Because we have an answer for this and we have an answer for this. We don't have an answer for that. So our strategy would be, let's take it in steps that we actually have a sense that we can do. So in this case, 396 Kelvin, and the formula for going from Kelvin to Celsius is what? Right, because we normally think of it as Kelvin is Celsius plus 273.15. So in that case, we work the formula around to say Celsius is equal to Kelvin minus 273.15. So 396 minus 273.15. So 723, 22.85. 122.85, yeah. 395, yes. Okay, so 122.85 Celsius. the precision of our initial number, okay, was at the ones place, right? There's no 0.2 or something like that. It goes only to the ones place. So since we're adding or subtracting, we're looking at precision, and our precision can only be as precise as our original number to the ones place. So this gets simplified to 120. We look at the ones place and decide where does it go from there. We look one place to the right of that. Is it 5 or greater? It is, so it rounds up. So 396 degrees Kelvin is equal to 123 degrees Celsius. So to understand both how to do it and why the answer is 123 as opposed to 122.85. Okay. How do we get there? Was through this math. How did we come up with 123 instead of 122.85? It's based upon the precision. The next step is to go from Celsius to Fahrenheit. Now you either have it memorized, the formula from Celsius to Fahrenheit, or you figure it based upon what we did before. Remember, it could be Celsius equals 5/9 Fahrenheit minus 32. 32 is 0. Yeah, okay. So this is the right format for Celsius to Fahrenheit. Now we need to convert it to look for Fahrenheit, right? Or you may have it memorized that Fahrenheit equals 9/5 Celsius plus 32 when you rearrange that formula. Let me check that real quick. So if I have 0 degrees Celsius, 9/5 times 0 is 0 plus 32 is 32. That's the freezing point. The formula's right. I can also check at 100. 9/5 times 100 would be 180 plus 32 is 212. Okay, that's the right formula. So to go from Fahrenheit, or from Celsius to Fahrenheit, that's my second formula. I've been given Celsius. I can just plug the Celsius in every time I see the Celsius and get my answer. Fahrenheit equals 9/5 Celsius. The Celsius is 123. So it's 9/5 times 123 plus 32. Key says that comes out to be 253. And again, we would still be looking at precision because I have it in 3 places, or to the ones place, excuse me. To the ones place, this would be rounded to the ones place. So 396 degrees Kelvin equals 123 degrees Celsius, which equals 253 degrees Fahrenheit. So let's think about the reasonability of that just for a second. 100 degrees Celsius is the boiling point, right? This is like 1/4 more than the boiling point. Boiling point is 212 in Fahrenheit. 1/4 of that, of 212, would be just a little bit more than 53. So we're looking for estimations. Is this reasonable? Yes, this is reasonable. Over here, 273, this was the easy conversion, right? From here to here. So I've got a high confidence this is right. If you're going to mess up somewhere, it's either going to be inaccurately applying within the signs, usually because of a negative number. That's why they gave you number 11 after 10, was to see if you'd catch that needed to be a -7 minus 32 on the last problem. And then the other problem is just the math here, but because how much you guys use calculators and stuff, that's usually a finger problem, not a concept problem. Okay, 9 divided by 5 times 132. And again, make sure you're using the calculator that you're going to use on the exam for the practice problems. So you get down all the monkey skills right. Because some calculators, if you put 9 divided by 5 times 132, it's going to treat it like this. In other calculators, if you put it in that order, it's going to treat it like different ways. So make sure you understand how your calculator is going to use what you enter into it. It's always a bad thing to have to figure out how to use your calculator during the exam. It's not a good time. Like especially when you take a standardized test and your calculator doesn't work, and so the person proctoring the exam gives you theirs to use. How do you think I know how that feels? It happened to me. I had to spend time making sure I was confident that the calculator worked correctly. and it's not fun. Or it worked correctly, that I was interfacing with it correctly. Questions on number 10? Process makes sense, hopefully? Even if you didn't get the right answers, the process of how to go from Kelvin to Celsius, Celsius to Fahrenheit? Okay. Here we go. Now, the class we did 2 days ago was a review of this, and that should have been posted as well. So if you still struggle with this after review it this morning, please go back and look at it. We spent almost a whole class period just doing these kind of problems. Okay. But we are going to do 7 and 8 right now. Converting the following into scientific notation, 12.45 with 3 zeros trailing. Let me write them all down here. 3,040,000. And then again, check me. My old eyes might see a comma when it's supposed to be a decimal, and vice versa. 6,100.500 and 0.001. 234. Okay, so we're taking these decimal forms and we're converting them into scientific notation, which means we're going to have something times 10 to the something, right? Strategy-wise, what do you suggest we do first? Somebody with a hand offer a suggestion. Yes, Ike? Okay, so the first step Ike wants to do is go ahead and move the decimal place one place over to the, so that there's only one digit in front of the decimal place, right? So in this instance, it's going to end up looking like 1.24500. We can start with times 10 to the what? How many places did you move it? One place to the left. So in order to keep it the same, we need to make this one higher, right? If I, just a little bit of math review, if I had just taken this number and written it over here, what would the exponent be? It's the same number, right? 12.45000, 12.45000. I could write this in scientific notation by taking the same number and writing it times 10 to the, no, to the 0. Because anything times 10 to the 0 is itself. Times 10 to the 0 is 1. Times 10 to the 1 is 10, right? Times 10 to the second is 100. So anything times 10 to the 0 is itself. It's a statement of unity. It's a 0. I mean, 10 to the 0 means it's 1. So anything times 10 to the 0 is itself. So that's the way we would start. If I move it 1 to the left, if I make it smaller, I need to make this bigger. And that's how we end up with 1.245000 times 10 to the first. So it's in the right form. We have accounted for the move through the exponent. Now the question is, what else do we need to check? One last thing. How many significant figures, right? Every significant figure from the original has to be represented in my answer. So we look at the first one. Process, non-zero digits. Any leadings? No. Any zeros between? No. Any trailing right of the decimal? Yes. All 3 of them are. So everything has to show up over here. So this is our answer. Let me get to the answer key. It always makes me feel better when they agree with me or I agree with them, whichever. Okay. Okay, for process-wise, let's go ahead and do this one. Let me just go ahead and write the same exact thing over here. If this helps you, great. If it doesn't, if you understood it before, I apologize if this is redundant, but let's start with times 10 to the 0. Okay? If we take the process we just mentioned, let's move the decimal place. Where is the decimal in this number at? It's implied to be at the end. It's implied, it's not present, so it's implied to be there. We need to move it so that it is just after the very first non-zero digit, which means we're going to do this in jumps of 3, but this is going to be 3, 6, right? 6 places. So if I were to write it like this, with the decimal here, 6 places to the left, I need to account for that by making this 6 higher. So I start at 0 and I count up 6. Now I need to go through and look at significant figures in my original and make sure that every significant figure is represented in my final. So process, we go through non-zeros. Leading zeros don't count, there are none. Zeros between significants, there. Zeros to the right of the decimal trailing, there are none. So those are not significant. So the only significant figures that need to be represented are the 3, 0, 4. This 0 here wasn't significant, was it? Right there. So it's just the 3, the 0, and the 4. And the only reason that 0 is significant is because it's between the 3 and the 4, which are significant. So that's my answer. You would get most partial credit, but you wouldn't get everything because it's not correct. I say that often throughout the course just to kind of nuance the difference. I would say that's true but not correct. In other words, you got to the right place, but you gave it a little bit more authority than you should have. You put too many places on it. So I know that you had the process to get there correctly. You forgot that little nuance of, precision versus significant figures. You didn't take that into account. So it's not technically completely accurate, but you got there in the right way. And you get the lion's share of the credit. Okay. Let me just go through the last two quickly. Excuse me. I'll write it again exactly as it is right now. I need to move 3 places to put it behind the first non-zero digit. Since I moved it to the left 3, I have to increase this by 3. Looking over here for the significant figures, the non-zeros, there are no leading zeros. Zeros between, trailing zeros right of the decimal place. I need to represent them all. So that is my answer. Lastly, write it just as it is. I have to move it to the left, to the right, 1, 2, 3 places. I account for that by making this smaller by 3, since I made the number bigger by a factor of 3. Now I need to make sure that all of my significant figures are represented. Looking over here, non-zeros, leading zeros are not, and that's it, I'm done. So 1, 2, 3, 4 has to be my answer. It is. There's my answer. Okay. So this represents the conversion from decimal format into scientific notation. The next question, number 8, moves us in the other direction. It moves us from scientific notation to decimal. So if there's no questions on these, it's just a question. Did this process of starting at 0 and counting it up or down, did that help anybody? Or is that something I should just ignore? Was it helpful at all? Okay, bobbles. Remember I said about bobbles? I need some feedback, yeses and nos. Was it helpful to show the 0 and move it up or down? Okay, thank you. Number 8, converting back to decimal. It's 6 times 10 to the 9th, 3.0450 times 10 to the negative third. Again, just keep checking me in the book. 1.56 times 10 to the 21st. Hoorah. And 4.5, 4 zeros, okay, 4.5 with 4 trailing zeros times 10 to the negative 7th. All right. I'm simply going to start with what I have. My coefficient is 6, and then how am I going to write this out? times 10 to the ninth. What does times 10 to the ninth mean for decimal? I'm going to move the decimal place. I'm moving it to the right. We're going from scientific to decimal. This means we need to make this bigger, right? So 6 has to become bigger than 6. We do that by moving it to the right. Since that's a positive, it's bigger. If it's negative, it's smaller. Okay? So when going from scientific notation to decimal, the positive does mean to the right, and the negative does mean to the left. Here it's 6, moving the decimal to the right 9 places. The way we move the decimal to the right 9 places, if there's an implied decimal there, is we're just going to write out 9 zeros. Right? What are my significant figures over here? It's just 6, right? Right there. Do I put a decimal place on there? No. If I put a decimal on there, what would that mean? A decimal means it has to have a trailing 0, right? Guess what? That would make that significant. That would make all of these significant. And that's not what we have here. We only have the 6 significant. The way we keep only the 6 significant is by not putting the decimal. Again, I hope the book agrees with me, because I go out there and assert all this stuff, and then, yep, we're good. So by convention, just to make it easier for us to see it, 6 billion. Okay. 3.0450 times 10 to the negative third. I have the number here, and I'm going to move the decimal 3 places to the left. 3 to the left. I'm just going to write several zeros in here as placeholders to see when I do this, when I move it. To the left, 1, 2, 3. I don't need that one. Okay. There's my new form in decimal form. Question is, do I need every one of those digits? We look over here. What are the significant digits? Non-zeros are significant. Zeros between are significant. Trailing zeros are significant. I need all of those. I have all of those. There's my decimal format right there. 1.56. I need to move the decimal place to the right 21 places. Okay? If I move it to here, that's 2 places, right? That's 2 places. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. The significant figures need to be 1, 5, and 6. 1, 5, and 6. I've got it. Again, if I were to do this and be presumptive, now every one of those is significant. Because if I did that, I'm telling you that my measurement measured all the way out to the ones place, and I estimated the tenths place. But if I leave it just like this, what I'm telling you is I measured to this place, and I estimated to this place. Huge difference. So again, by sets of 3, that's our number in decimal format. And lastly, 4.5, 4 trailing zeros. Moving at 7 to the left. Let me just draw a bunch of zeros here to see if we can get placeholders in place. We'll see how many we need in a minute. Moving at 7 to the left. 1, 2, 3, 4, 5, 6, 7. I don't need this one. My new decimal place is there. I lose this. And I need to make sure that those are both significant. No leadings, no mids, and all trailing. I need to have all of those represented in my answer. 4, 5, and 4 zeros. 4, 5, and 4 zeros. I'm done. Those have to be there as significant trailing zeros because they're in my original number as significant.